Santosh, a sophomore from Electrical Engineering Department of IITM. My presentation is on the topic of history of Apollo guidance computer as a part of E5004. The contents of this presentation. First, we'll go over the different components of AGC and find out what AGC is. Then we'll say about the development of AGC and the people and the organizations behind it. Then finally, we'll study the impact of AGC on hardware and software sides of engineering. AGC and overview. So the Apollo guidance computer is basically a digital computer. It was produced for the Apollo series of missions in the 1960s. It was installed on both the command module and lunar module of the Apollo spacecrafts. It was designed at MIT Instrumentation Laboratory under Charles Draper. The hardware design part was led by Eldon Seahar, and the software design part of the Apollo guidance computer was led by Margaret Hamilton. So this was the first computer ever to be based on silicon integrated circuits. Some basic features of the AGC. It weighs around 32 kilograms and it took up around 1 cubic feet. It consumed a very small amount of power, around just 70 watts at 28 volts DC. So these stats were much less compared to other computers in the same time, like the mainframes and other power-hungry computers, which weighed a lot and which took up a lot of space. It can execute around 100,000 instructions per second, and the base clock speed of Apollo guidance computer is around 1 megahertz. So the given diagram, we can see the basic blueprint of the complex and lunar module. We can see the Apollo guidance computer along with some other different input and output devices like inertial measurement unit IMU, thrusters and others. So this Apollo guidance computer is the brain of the lunar module. It takes in inputs from all these input devices like IMU and then it provides the required output using the output devices like the display and the thrusters and etc. Hardware of AGC. So the digital circuitry of the Apollo guidance computer contains entirely of 3 input NOR gates, and each flat pack contains 2 of these NOR gates. So a group of 60 flat packs are taken together and they can be made into a logic module. And 24 of these logic modules are placed together in a structure called trace. So in the image on the left, we can see a single flat pack. It's basically an IC which contains 2 3-input NOR gates. And the image and in the second image, we can see these 60 of these single flat pack can be stacked together to form a logic module. The circuitry of AGC was placed in 2 trays. Tray A and Tray B. So Tray A held all the logic circuits, interfaces and the power supply required for the AGC, and Tray B had the memory electronics, analog alarm devices and the clock. All units of the computer were sealed. So in the given image we can see the 2 trays of the Apollo guidance computer which contains 24 logic modules each and all the digital circuitry required. Now let's see about the memory of AGC. It has both ROM, fixed memory, and RAM, erasable memory. It has 36,000 words of ROM and 2,000 words of RAM. So the fixed memory, it contains the software which is needed to guide the craft and land it properly. As it is stored in the ROM because we don't need to erase it. And RAM was used to store the intermediate results of calculations like the velocity of the spacecraft, the position, and others. The memory word length, each word in the memory of Apollo guidance computer was 16 bits. It consists of 15 bits of data and 1 sign bit. The internal, each memory word in the CPU internal is also 16-bit word, but it contains 14 bits of the 16 bits is allocated to data and 1 bit is a sign bit and the other is the overflow bit. Fixed memory of AGC. The fixed memory of AGC is a rope memory where wide threads and tiny donut-shaped magnetic cores represent bits of information. So the fixed memory contains a series of cores and threads. The orientation, the way in which the thread is moved around the core determines whether whether the bit represents 1 or 0. The core with a wire threaded through the center represents an 1 and an empty core represents an 0. By this way we can hard code a series of 1s and 0s. We can hard code instructions as a series of 1s and 0s into the fixed memory of the uploaded computer. Erasable memory of the AGC. It contains of coincident current ferrite cores. These cores are covered by silastic. It's silicon rubber, and then again it's covered by epoxy for further protection. Input output devices. The different input output devices connected to the upload guidance computer are: first one is the IMU. IMU basically provides all the acceleration, the angular gyro data, and sextants and telescopes. These are used for navigation and sightings. So these devices are basically used to set the direction, to guide the upload guidance, to guide the spacecraft in the right direction. And radars and ranging equipment. So these radars and ranging equipment measure how far is the spacecraft from the surface of the target, and provide the data to the AGC. And engines, thrusters, and descent control systems. All the others are the output devices, which, according to the inputs provided to the AGC calculates the required thrust, required velocity, and everything else. And then the thrusters and other output devices are operated accordingly. So descent control system, DCS thrusters and reaction control system thrusters are output devices, and it also has analog displays to display the altitude and range of the spacecraft. And it has a special device called display keyboards or disk keys. Two disk keys are present in the command module, and one is present in the LUDAR module. The disk key. It represents to the Apollo display and keyboard unit. It is the primary form of input to the Apollo guidance computer from the astronauts. Astronauts used to enter the instructions and commands to the AGC from the disk key, and this key also contains displays to display the altitude, range, and other important data to the astronauts. So commands entered to the Apollo guidance computer consist of two parts: the work part and the noun part. So work part basically it means an action to display or update, to print something like that. And the noun part is basically a value in which an action can be performed. So examples of nouns are velocity, angles, times, and rates. So in order to enter a command to display velocities, the verb part of the command is display. So a particular numeric 2-digit number is allotted for the particular verb, and for the velocity a different 2-digit number is allotted. So the astronaut has to enter the 2-digit number for each verb and the noun into the disk key to display the velocity, to make the upload guidance computer display the velocity. It contains a numerical keyboard to enter the commands into the AGC, along with other important buttons like enter, restart, and much more. So from in the given diagram, we can see a schematic view of disk key. It contains all the numbers, plus, minus, and some important commands like clear, enter, reset, and others. It also contains a display to display all the different values. And one more thing is, it cannot display floating point values. It can only display whole numbers. And now let's move on to the software part of Apollo guidance computer. Apollo guidance computer was entirely programmed in the AGC assembly language and an interpreter. This interpreter converts the AGC code to mission readable code. It has a rich instruction set with matrix and vector operations, and with double and triple precision floating points. So each instruction, it took around 26 milliseconds to run, and the code which is used to program the command module and LUDAR module is available on GitHub, and it has been made open source. So the basic principle of the Apollo guidance, basic software principle of the Apollo guidance computer is a priority interrupt real-time operating system. So the software develops different operations the computer needs to perform as jobs and sorts them in the order of priority. So the jobs get done in the order of priority. Several jobs can run at a time, but only the highest priority job can make use of the disk key. Scheduling a new job and prioritizing. So starting a program requires some temporary storage to be allocated. There are two types of storage area available, the core set and the VAC area. There are 6 courses and 6 VAC areas available to initialize new jobs. As all jobs are assigned a priority, only the highest priority job can use the disk key. As once the highest priority jobs get done, the upload guidance computer moves on to perform all the lowest priority jobs and clears the queue. Cooperative multitasking and error recovery. So each task when it's run by the upload guidance computer, it checks a variable called new job every 20 milliseconds to check if there are any other jobs in the queue, any other jobs waiting to run. So if the job which is currently running, if it reaches a known favorable state, it is called a checkpoint and the state of the program is saved. State in the sense all the values of different variables are saved. And if the new job has not been checked for 640 milliseconds, the hardware triggers a restart and the system starts from the save checkpoint. So as every time new job is checked every 20 milliseconds, in case if a program hangs in the middle or if it causes some trouble, the new job variable won't be checked and there is an inbuilt condition which says that if the new job is not checked for 640 milliseconds, a hardware reset is triggered and the system starts again from the save checkpoint. So in case of any critical error, during landing or during the mission, this safety mechanism makes sure that a favorable checkpoint of the program is stored and then it restarts the entire system so that it can continue from the saved checkpoint and proceed to recover from the error. The upload landing alarms. This exact same thing happened in the during the landing of upload alarm. So during the landing, the 1201 and 1202 alarms kept on occurring due to some unnecessary tasks which pushed the AGC to full capacity. So essentially the queue of AGC, the memory of AGC was overloaded with some unnecessary tasks during the landing. So these overflow errors 1201 and 1202 kept on coming during the landing. So the crew decided to restart the upload guidance computer. So the guidance, navigation and targeting data which was saved from the last checkpoint of the upload guidance computer was saved, and then after the restart the program continued from the save checkpoints, and then the landing was successful. Now let's have a look at the development of AGC and the people and the organizations behind them. So the instrumentation laboratory of MIT worked on small aerospace computers since the late 1950s. So from the 1950s they started working on some small aerospace computers like Dr. Raymond Alonso from MIT. He developed a small computer in 1958 and 59. Soon after, Eldon Hall also developed a small flight computer for some unmanned mission. And as these developments kept on coming, and after the NASA has decided on the Apollo missions, they decided to use a computer on board because the landing conditions can be unexpected and decisions need to be taken very fast. So a human cannot always interfere and take decisions for spacecraft. So they decided they need to have a computer on board, and thus the decision to develop Apollo guidance computer was taken by NASA. In 1961, NASA contracted with the MIT Instrumentation Lab to design, develop and construct the hardware and software of the Apollo guidance computer. Milton Trageser was appointed as the project manager and David Berg was appointed as the technical director. This was the start of MIT NASA partnership, which was key to success of the Apollo series of missions. A brief note on Eldon Seagull. He was the lead designer of the Apollo guidance computer. He began working at the MIT Instrumentation Laboratory in 1952 after his physics PhD in Harvard. So before the Apollo guidance computer, he worked on the guidance systems of submarine launched Polaris missiles, also in MIT, and then he moved on to the Apollo project in 1961. He was the first one to propose the idea of using integrated circuits to develop AGC, which was a bold move because integrated circuits were a very new. Integrated circuits were an entirely new idea to the market, and he was the first one to propose using them to make the computer. A brief note on Margaret Hamilton. She was the first programmer hired for the Apollo project, and later she became the director of the software engineering division of the AGC in 1965. She studied mathematics in the University of Michigan in 1955, and then she got transferred to Elkhorn College. She earned a BA in math with minor in philosophy in 1958. Before working on the Apollo project, she worked on a project called Semi-Automatic Ground Environment in MIT Lincoln Lab. SAGE was a project related to missile tracking and missile detection systems. And after she became the head of software engineering division, she was the person responsible for the entire team who wrote the entire code for AGC, and also tested, including the error detection and recovery software. The impact of AGC on engineering. So in the 1950s, the norm was bulky computers which took up entire rooms and consumed a lot of power. So as spacecrafts need to be lightweight, we cannot use those computers to onboard these spacecrafts. So this motivated Apollo guidance computer engineers to develop much lighter, smaller, and faster computers. So the trend of making computers lighter and faster started during this era, and this has continued throughout in the 1970s and 80s, leading to much faster and smaller computers as time progresses. Impact of AGC on hardware. So it was the first flight computer to use integrated circuits, and after the success of the Apollo 11 mission, after the success of the first moon landing in 1961, it popularized the use of digital circuits in place of analog circuits. This was a pivotal point in transition from analog to digital circuits and led to a boom in the field of computer architecture and led to development of much more advanced computers during the 1970s, 80s and so on. And the disk key of the Apollo guidance computer can be seen as the precursor of the keyboard and input devices we use nowadays. And it was the first. So disk key can be considered as the precursor of the keyboard and mouse we use today, and it pioneered the whole field of the user-computer interaction. Impact on software principles. The code written for AGC is the earliest written real-time operating system. So the software engineers behind AGC, they pioneered the idea of converting tasks into jobs and prioritizing them. This gave rise to the idea of priority interrupt multitasking. The software written for AGC and the way it handled program alarms, during the moon landing, it proved to all of us that error handling, exception handling, and software validation are as important as the code we write. And here are some references which I used.